In this video, I'm going to talk about estimating a mean value of y and predicting an individual value of y for simple linear regression. If we think back to chapter 1, we made a distinction between calculating a confidence interval for a univariate population mean E of y and calculating a prediction interval for an individual univariate y value. And you may recall these formulas that we used. For the confidence interval for the mean, we had it centered at the sample mean, and then plus or minus a t percentile times the sample standard deviation divided by the square root of n. And we call this quantity here, the sample standard deviation divided by the square root of n, we call that the standard error. And then we contrasted that with the prediction interval for an individual y value. It had a similar form, so centered at the sample mean plus or minus a t percentile times a standard error. But this standard error had the formula given by sample standard deviation times the square root of 1 plus 1 over n. And that made this interval wider than this interval, and we rationalize that because it's much harder to predict an individual y value than to estimate a mean. So we have a similar distinction between confidence and prediction intervals in simple linear regression. Things get a little bit more complicated, but the essential distinction is the same. So a confidence interval for the population mean at a particular x value is given by centered at y hat, so that's the predicted value for the mean, plus or minus a t percentile times this thing here, which is denoted s y hat, and this is the standard error of estimation. A prediction interval for an individual y value at a particular x value has a similar form. It's centered at y hat, and I've put a star by it just so that we know that it's a prediction rather than an estimate of a mean. So we're predicting an individual y value rather than estimating the population mean. And then plus or minus a t percentile times this quantity, which is the standard error of prediction, and it's denoted s y hat star. Okay, so these two formulas look similar. The main distinction is this is the standard error of estimation and this is the standard error of prediction. The standard error of prediction is always larger than the standard error of estimation, and so this prediction interval is always wider than this confidence interval, and that's because it's much harder to estimate. It's much harder to predict an individual y value than it is to estimate the mean E of y. Okay, let's go through the confidence interval for the population mean E of y in a little more detail. So here's the general formula, and I've also given you the formula for the standard error of estimation. So it looks pretty intimidating, but we're not going to worry too much about the details of it because we're simply going to obtain this number using software. But I do want to present the formula here because we're going to see why the standard error of prediction is wider than this standard error of estimation. So that's why I've got the formula here. And the other reason for having the formula here is because we can see what things affect how wide or narrow the interval is. So what tends to make the interval narrower or more precise is when the sample size is large, when the particular value of x that we're evaluating the interval at is close to its sample mean. So you can see that this piece of the formula would be small if that was the case. When the regression standard error s is small, so that's this piece of the formula. And then for lower levels of confidence, because a 90% confidence interval is going to be narrower than a 95% confidence interval. So, as an example, for the home prices floor size data set, the 95% confidence interval for the mean of y when x equals 2 goes from 267.7 up to 276.1. So let me just show you how we can get that. So we can just run this piece of code, and here's the confidence interval right here, 267.7 up to 276.1. And how do we interpret that interval? Well, we can say we're 95% confident that average sale price, because this is a confidence interval for the mean, so average sale price is between $267,700 and $276,100 for 2,000 square foot homes. Okay. Let's contrast that with a prediction interval for an individual y value. Okay, same basic structure for the formula, only this time the standard error of prediction has this formula. Okay, and if we just quickly go back to the standard error of estimation, okay, it's this, and then we look at the standard error of prediction. The difference is that there's an extra 1 inside the square root. So that makes this standard error of prediction always a larger number than the standard error of estimation. Same features make the interval narrower, however. So again, when the sample size is large, when XP is close to its sample mean, when the regression error, standard error, is small, and for lower levels of confidence. So the same factors would make the interval narrower as made the confidence interval narrower. Okay, and as I mentioned, since the prediction standard error is always larger than the estimation standard error, the prediction interval is always wider than the confidence interval at a particular x value. So let's see how that works for the home prices floor size data set. So again, let's use R to get that. So it's this bit of code here. And now I get an interval going from 262.1 up to 281.7. And we interpret that by saying we're 95% confident that the sale price for an individual 2,000 square foot home is between $262,100 and $281,700. And that's a wider interval than the corresponding confidence interval for the mean. Remember, that went from 267.7 up to 276.1. The prediction interval goes from 262.1 up to 281.7. It's much wider. And here's, I'm going to come back to that question, but here's an illustration of that phenomenon, that confidence intervals for the mean are always narrower than prediction intervals for individual y values. So here I've got a scatter plot of a generic data set with y on the vertical axis, x on the horizontal axis. We've got a regression line given by the solid line, and then I've got a confidence intervals for the mean at each value of x given by the dashed lines. Okay, so those are quite tight around the regression line, and by contrast the prediction intervals given by the dotted lines are much wider. Okay, and then the other thing that you can see in this graph is, if you, particularly with the confidence intervals, they're narrower close to the middle of the range of x, and they're much wider at the extremes. And that's because of this phenomenon here. The interval tends to be narrower when xp is closer to its sample mean. Okay, and then just to finish up, I just want to go back to that question that was posed at the end that I skipped over. What is a 95% prediction interval for large n? So for really large samples, what does this formula become? So if n was really large, what would happen to all the pieces of this formula? Well, 1 is just a constant. 1 over n, for very large n, that's going to get very close to 0. And then what about this part of the formula? If n was very large, we would have this sum of lots of squared things on the bottom and just one squared thing on the top. This is going to get close to 0 as well if n is very large. Okay, so both these pieces are going to be very close to 0. So for very large n, this standard error of prediction is going to be essentially s times the square root of 1 plus a very small number. So that's going to be very close to s. So the formula is going to simplify to y hat star plus or minus t percentile times s. And what is the t percentile for very large n for a 95% interval? Well, as the degrees of freedom for a t distribution get very large, the distribution becomes more and more like a normal distribution. And the 97.5th percentile of a normal distribution is 1.96. So this formula simplifies to y hat star plus or minus 1.96 times s. And if I just round that to y hat plus or minus 2s, that should remind you of how we interpreted the regression standard error s when we talked about it in an earlier video. We said one way to interpret s is to multiply it by 2, and that will give us an approximate prediction interval. And this is where that result is coming from. So that's estimation and prediction for simple linear regression, and the distinction between confidence intervals for the mean and prediction intervals for an individual y value. And practically speaking, a confidence interval for the mean is if we are wanting to find the average sale price for a particular size of home. Okay, so for example, we might have 10 homes, 10 2,000 square foot homes, and we're trying to estimate the average sale price for those 10 homes. We can narrow it down to this interval here. By contrast, if I was just trying to predict the sale price for one of those homes, that's a harder task, and so our interval is wider. So in the next video, I'm going to run through a complete simple linear regression analysis for a larger data set.